Hello everyone, and today we're going to start Chapter 8, AC Steady State Analysis. In this chapter, we wanted to first review basic sinusoidal functions. And we also wanted to know how phasor works and how to draw phasor diagram. We want to know how to calculate impedance and admittance for basic circuits and elements. And we want to know how to combine impedances and admittances in series and parallel circuits. Finally, we wanted to know how to apply our circuit analysis techniques that we learned in earlier chapters for resistive circuits to frequency domain circuits, where the circuits includes resistors, inductors, and capacitors. So now first let's look at sinusoidal functions. Let's see if we have a function x omega t, and that is equal to a value that is the maximum value it can reach and multiply by sine of omega t. We call the omega t argument of this function. And the maximum value it can reach, we call this amplitude. If we want to plot it, and the x-coordinate, we're going to use the omega t, the argument. And this is the function. And the function looks like this. And you see that the maximum value you can reach, this is the mx, this is the xm, which is the amplitude. And for one cycle, you see the function go up from 0, increases to maximum, and then down to 0, then go to the negative maximum, and then go back up to 0. This is for one cycle, and it takes this one period. We call this 2 pi. Now you see the function repeats itself after that one cycle, and again it will go up again, go down, go to the maximum, and back up to 0. And this is what we call a period. So if I plot it and using time as the x-coordinate here, t, the same figure repeats itself. But this time we call the cycle here, it takes time capital T, that much of time. Remember, this is time now. This is what we call a period. Now, how often in 1 second, how many of the cycles are going to appear? This is what we call this a frequency. F is 1 over period, which is the omega divided by 2 pi. And we know that omega is angular frequency, which is 2 pi times f. Now, f has a unit of hertz. Whenever the problem given 60 hertz or anything, this is referring to f. in the sinusoidal calculation, when we need omega, we need to remember to multiply by 2 pi. We notice that the function repeats itself after time is equal to capital T. So for the periodic function, we have x omega t plus capital T. You're going to go back to the same function, and that is equal to x omega t. For phase angle, so let's look at another term that we call phase angle. If the sine function doesn't start at 0, so for example, I have x1 is equal to a maximum value that I call xm1 times sine omega t plus theta. And then I have another function x2 that is equal to xm2 times sine omega plus phi. And this is what we call phase angle. This is what we call phase angle. Now, if theta equals phi, then we call they're in phase. x1 and x2, they're in phase. Now, if theta does not equal to phi, and we call them out of phase. Now, depending on the theta and phi, their value, and we can call one is ahead of the other, and we call this in lead. So for example, if theta is equal to 0, if theta is equal to 0, phi is equal to pi over 2. Let's plot it. For theta equal to 0, we have a sine function like this. And for phi is equal to pi over 2, which is 90 degrees. Then we can see that when t equals 0, the sine pi 90 is already here, is 1. Let's imagine they're equal. The x1 m is equal to x2 m. They both have the same magnitude. So the sine function for the x2 is going to be like this. And we call that phi is in lead. And so x2 leads x1. Let's look at the example here. We have 3 functions here. We have v1, which is the voltage 1, is equal to 4 times sine 377 t plus 25 degrees volts. And we notice that 4 is the amplitude of v1, and 25 degrees is the phase angle. 377 is omega. Now there are 2 currents. One is the I1. I1 is equal to 0.05 cosine 377 t minus 20 degrees. And then the I2 is equal to negative 0.1 sine 377t plus 45 degrees. And we want to determine, by comparing the phase angles, we want to know by how much the V1 leads I1 and V1 leads I2. Remember the term, we're saying V1 leads I1. It could be negative, it actually lags if it's behind. So here, what we need is we actually need to review some trigonometry identities here. We wanted to remember or review that sine omega t is equal to cosine omega t minus pi over 2. Or we can say cosine omega t is equal to sine omega t plus pi over 2. And this actually is illustrated by the example we saw earlier. And you can see here this x2, this x2 here, phi is equal to pi over 2. So the function we have, the x2 here, this is x2. The x2 is equal to, if you remember, we gave that example, is the xm2, the amplitude times sine omega t plus phi, where the example here, the phi is equal to pi over 2. Now this is exactly what the cosine function look like, right? So if we look from 0 here, that's a cosine function. So this is one set of the identity that we wanted to remember, and it's going to be very handy when we're converting from sine to cosine. The other one is negative sine omega t. That is equal to sine omega t plus or minus. It depends on the need, depends on what we wanted to express that into. 180 degrees. Remember, 180 degrees is pi. That's a conversion between degree to radians. And then negative cosine omega t is equal to cosine omega t plus minus 180 degrees, or pi. So that's another set of identities that we need frequently. So we're going to put this aside. So we're going to see this particular problem here. We know V1 is equal to 4 times sine omega t plus 25 degrees. So the phase angle of V1 is 25. So I'm going to say V1, theta V1, the phase angle of V1 is equal to 25 degrees. Now we want to compare that theta I1. This is equal to negative 20 degrees. But we notice that we really can't use an equal to 20 because the I1 is given by cosine function. So for this one, if we really truly compare the angle, we can't compare 25 to 20 because 25 degrees is coming from the sine function, where the negative 20 is from cosine function. So what we really have to do is we really can't use that. That's not okay. We really have to convert the I1 into a sine function. So that 0.05, as we just reviewed, cosine function, that now we want to convert it to sine function. So that's equal to sine omega t, which is the same 377t, and minus 20 degrees. That what was the original argument here. But we need to plus a pi over 2, which is we need to plus 90. And so now we'll actually end up with 0.05 sine omega t, which is, let's just use omega t, which we know what omega is. But now it's actually is plus 70 degrees. Now we can compare the V1 as a sine function and I1 also as a sine function. So we can safely see now theta I1 in this case is 70 degrees. Now, before we actually do the comparison, who leads, V1 leads by I1 by how much? Let's convert I2. The reason we need to convert that is we notice that I2 has a negative sign. It's a negative sign. So we use the second pair of identity that we wanted to get rid of the negative sign. And we have that's positive 0.1 times sine 377t plus 45. That was the original given. And now you can see what we need here is plus minus 180 degrees. Now we want a minus 180 degrees because we wanted the angle, try to make the angle smaller than 180 degrees. So we're going to minus 180 degrees. And in that case, we end up with 0.1 times sine the omega t. Again, we know the omega. Then minus 135 degrees. So now we're ready. We know that V theta I2 is equal to negative 135 degrees. So, by how much V1 leads? We can say V1, the theta V1 now, minus theta I1 is equal to 25 minus 70 degrees. That is equal to negative 45 degrees. So you can see the V1 leads V1 leads I1 by negative 45. So actually, in other words, we can say I1 actually leads V1 by positive 45 degrees. So in reality, the I1 is in lead. Now similarly, we can look at the relation between V1 and I2. So I'm going to theta V2, theta V1 minus theta I2 is equal to 25 degrees minus 135 degrees. And we end up with a positive 160 degrees. So we say that V1 leads I2 by 160 degrees. So that's the angle relationship, phase angle relationship that later on we're going to frequently encounter.